Okay, great. Well, thank you, everybody. I'm very excited to be back here in Sao Paulo. I was here about 2 years ago, and it's a wonderful place, so thank you to Roberto for inviting me. I had originally planned to talk about some of the real forecasting modeling that we have been doing for influenza, but given the current coronavirus epidemic, I decided to change my talk slightly, although I will be talking a little bit about the influenza forecasting modeling activities we have been doing. I will touch on it a little bit at the end, and I will kind of focus on some of the planning for pandemic influenza, and which I think that a lot of the modeling that we did for influenza is going to apply for coronavirus, and so I wanted to just discuss some of the mitigation strategies that we have explored in the past. So this is also the work of a lot of people in our team that have been working on many of these models, so I like to thank them also for contributing to some of the figures and the approaches that I'm going to be presenting. So the goal, okay, I think I can use this. Yeah, okay. So our main focus for our team has been on improving decision support by understanding, modeling, and forecasting infectious diseases. And the approach that we have taken is to use different types of data and different types of models to understand and forecast diseases and to quantify uncertainty. And what we really want is the holy grail. People think that we have a crystal ball and then we can just tell them the future, but in reality, we don't really have that. And you see this over and over again when, especially now during the coronavirus, they say, when is coronavirus going to be spreading in my community? How many people are going to die? And we as mathematicians, we don't really have a crystal ball, right? But a realistic alternative is to provide an accurate, quantitative, and uncertain forecast after a few cases have appeared in a community. And this is very similar to what we have for hurricane forecasting, where when you see a tropical storm in the ocean, you can use that information to determine whether that tropical storm is going to become a hurricane, but you don't really know when the next tropical storm will show up in the ocean. And so those are the kind of approaches that we're trying to take. And one of the things that we feel that is going to help the mathematical community is the use of heterogeneous data streams. And by heterogeneous data streams, I mean all kinds of different data, because we don't really know what's happening in every single community around the globe. But we can exploit and leverage different data such as climate data, census data, social media, and many other data streams to help us achieve this goal. So the approach I've taken and we have taken in our team follows kind of this dynamics, and we have been borrowing a lot of approaches from the weather forecasting community to see if we can apply those approaches to infectious disease modeling. And if you're familiar with weather forecasting, they use data from all over the world. They have sensors, they have satellites, they have ground sensors, they have sensors around the ocean that capture precipitation, wind, temperature, and many other things that are used in combination with models to forecast the weather, to forecast hurricanes, to forecast storms. And we feel that these kinds of approaches can also be used for modeling infectious diseases. And so it's a combination of data-driven and model-driven approaches to help us understand what's going on in a community. So I'm going to start by talking about some of the work that we did on the emerging behaviors during the H1N1 pandemic, and this was during the 2009-2010 pandemic, the swine flu. And so we started by trying to understand what people were doing in response to this pandemic. And so the approach, which follows a very similar dynamics as what I presented before, we use Twitter data, clinical surveillance data, census data, in combination with agent-based simulations to understand the impact of face masks and also other mitigation strategies. And so the question that we first had was, what type of behaviors people adopt during an outbreak? What are people doing? We had seen a lot of pictures of people wearing face masks, and we traveled from the US, and so basically I was wearing a face mask during, while I was at the airport, and we have, and one thing that you need to know is that, if you use a face mask and you get it dirty or wet, you should throw it away. But I wanted to know the impact of face masks on the spread of H1N1. But the challenge that we had was that there's no database to quantify the emergent behavior that people are adopting during a pandemic. We have surveillance systems, and we have databases that can tell you how many cases are appearing in a community. You have number of hospitalizations, you have number of people that are dying, and sometimes you also have vaccinations, how many vaccinations are being implemented in a community, but you don't really know anything about behavior. And so how would you know how many people are wearing face masks or are washing their hands or are using hand sanitizers? And so we decided to explore the potential use of social media to see if we could quantify the use and quantify emergent behavior during pandemic H1N1. And so we started exploring Twitter, and as you know, I don't know if many of you are Twitter users, but during 2009, 2010, there were about 10,000 tweets per hour about the swine flu. And so we decided to identify and extract information related to flu, and specifically we wanted to know what kind of behaviors people were adopting during the pandemic. And some of the behaviors that we looked at included face mask usage and hygiene, including hand washing or also using hand sanitizers. And so we wanted to use this information to inform our models so that we could say, if 20% of the population are using these types of mitigation strategies, then this is going to be the impact on disease. And so here I'm showing a figure, and in red, let's see if this, okay, so here in red, it's the CDC influenza-like illness data. So basically it's the number of cases of influenza-like illness in the United States. And then in blue we had two types of behaviors. We decided to classify face masks by people just mentioning face masks or people observing other people wearing face masks. And so basically we classified the tweets by, some people were just talking about, there's a shortage of face masks, or I would like to buy a face mask, and those are mentions. Whereas the other one, which is the solid line, is people seeing other people wearing a face mask. They could say, I saw someone in the subway wearing a face mask, and so that's the difference. So one thing that you can, it's clear from this picture is that as the number of cases increase, the number of people on Twitter talking about face masks also increase, and as the number of cases decrease, so did the mentions on Twitter. And so this is important because then there was a clear correlation in the use of face masks and the mentions of face masks on Twitter and cases. And so, okay, well, now we know that people are talking about face masks, but we didn't really know where these people were. And so one of the challenges was, if we wanted to model the impact of face mask usage in the United States, we also needed to know where people were tweeting from. And because we know that behavior is not demographically and geographically uniform, there may be some areas where people are more likely to wear face masks than in other areas, and so we wanted to account for that differentiation. And so we went ahead and decided to build a model that could help us infer location for the tweets. And so basically here, we are using, each tweet comes with many different fields, such as user location, user time zone, the text, user description, and the language of the tweet. And so we use this type of information to help us identify where people were tweeting from. The two fields that were most useful in telling us where people were tweeting from were user time zone and user location. And some people actually enter their location. They can say, Sao Paulo, Brazil. But some people enter, in the bathroom or in the kitchen as their location, which is not very useful. But because Twitter stamps each tweet by the time zone, then we could actually determine whether people were, at least in the United States, the East Coast, the West Coast, in Central, or at least we could identify where they were within the U.S., and then we could use that information to account for the location. And another important information that we wanted to also capture was the demographics of the people that were tweeting, which we didn't. There are several researchers out there that are also trying to infer demographics based on the tweets and based on how people talk, or based on the name. They can infer whether it's a female or a male. But instead, we decided to take a different approach. And in order to determine who was changing behavior, we performed a systematic literature review based on small surveys of behavior change during different epidemics. And we wanted to determine the age and the gender of these populations, to see are men or women more likely to adopt behavior, or what age groups are more likely to change their behavior. At the end of the study, we were only able to use the gender because the age groups were very different across the different studies. Everybody used let's say 18 to 24, and some people use 18 to 60, and so it was hard to do it systematically. So we ended up only accounting for gender. And here I'm showing the results of our study, which says that women are 50% more likely than men to adopt non-pharmaceutical interventions. And by non-pharmaceutical interventions, I mean hand washing, hand sanitizing, wearing face masks, and social distancing, quarantining, and isolation. And in comparison, men were about 12% more likely than women to adopt pharmaceutical interventions, and by that I mean vaccines or treatments. And so this information was useful for us because now we could take all these different pieces. It's like a puzzle. It would be great to have all the data that you need to model, but because we don't, then we have to get different information from different studies and different data sources in order to perform our analysis. And so then we were kind of ready now to start modeling the impact of face masks in a community. And we decided that behavior change was dependent on age and gender. And although we didn't perform a systematic literature review on the age, our initial analysis indicated that the older people are, the more likely they are to change their behavior, and younger people are less likely to change their behavior. And so we also decided to account for changes in susceptibility and infectivity. As we know, it is recommended that if you're sick, you should wear a face mask, but we also wanted to see if people are not sick and they want to wear a face mask just to protect themselves from touching their mouths or their noses, we wanted to see what impact it could have on the community. We also decided to account for different compliance rates, which is the acceptance rates, and geographic differentiation, because we knew from analyzing Twitter data that people were talking about face masks differently across the United States. And so here I'm just showing you an example of some of the runs that we perform. And basically, we had different age groups. You have female and male. This is effectiveness to others, and this is effectiveness to self. And so it's how much are you protecting yourself from, if you are not infected and you're wearing a face mask, how much are you protecting yourself? And then effectiveness to others is, if you are infected and you're wearing a face mask, what percentage of, what's the probability that you're going to infect others? And then we had different acceptance rates, and basically here is saying that younger people have lowered compliance rates or acceptance rates, and older people have higher compliance rates. And so once we had all this information, then we used an agent-based simulation to perform this study. And so basically, we have a large simulation of the United States. And the simulation consists of 3 different components, and here are the 3 different components. One is geographic information, so we have the entire United States in a simulation where we have households and schools and parks and recreational areas. And then, and that's obviously based on a database that we have with all the addresses for the United States. We also have a synthetic population, and the synthetic population corresponds to the United States population of about 300 million people. And each person in our simulation has a specific demographics. And so based on those demographics, that's how we're going to assign the behavior changes. And in addition to the synthetic population, the final piece is movement or itineraries. So once we have 300 million people in our simulation, each person is going to have to carry out a certain number of activities throughout the day. If you're if you're the head of a household, you probably go to work, and then you go and take lunch, and then you go back home. And if you're a child, you're probably going to go to school, and you're going to perform different activities.
I have a question for
yes.
you. The beauty about dealing with data, that's true for every problem I know how you do here, you only can deal with the data that you have.
Right.
But you have modeling at the same time.
Mm-hmm.
How do you account for if the data is sufficient, and for the stuff you don't have, how you put into modeling? How do you play that game?
Well, we have, all our models are limited by the data that we have, right? And so when we don't have data, then what we typically do is we explore many different scenarios. So for example, if we don't really know how many people are going to be isolated or are going to be quarantined, then you play different hypothetical scenarios, and you say, what if 10%, 20%, 30%, because we don't really have that information. If we do have some studies that have shown, maybe 10% of the population quarantine for a specific epidemic, then you can use that information to kind of inform your parameters. But for parameters that we don't have, then we just explore a distribution and a whole number of scenarios, and then that's how we go about. So, okay, I guess, so now let me see if I can show you. So this is a simulation of how the disease spreads in the United States for different, oh, sorry. Okay. Okay, for different, in different activities. So you have work, home, shop, visit, social, other, and school. And you can kind of see how the disease is spreading for a given epidemic simulation. And so one of the things that we found is that there's geographic differentiation in the simulation. It doesn't spread equally across the United States, which is what you would expect because every area has different activities and the disease is spreading differently. But here I'm just showing California, and I don't know if, for those of you who may be familiar with California, Beverly Hills is here along this coast. And I forgot to include the different values for the different colors, but the epidemic is lower for green dots, and then it goes, then the next one it's kind of light green, and then yellow, and then red. And so the areas that are red are areas that have higher number of cases, and the areas that are green have the least number of cases. And you can see here there's some hot spots. And so one of the things that we wanted to know is why are there certain hot spots in some areas and not in other areas. And so we looked at different demographics and to see if the demographics were driving these hot spots. And it turns out that the presence of children increases the probability of infection. And I think there's been many, many studies that have shown that children are transmitters and sources of infection because they tend to have very close contacts with each other. And so then they bring those infections home, and then those people that are home bring those infections to work, and so on and so forth. So the presence of children is one important factor. The size of household, the household size was also the most important driver of the disease. And it turns out that the household size for the mansions along the Beverly Hills and all the rich areas in California, the household size is about 2, whereas the household size in areas such as Santa Ana, which is around here, are over 4 and 5. And so the more people you have in a household, then the more likely that you're going to have a higher infection rate. Yes?
So are those hotspots that are predicted by the model or hotspots that you see in the data?
So the hotspots were predicted by the model, and then we went and compared our results against data, clinical surveillance data, and it confirmed what the model was saying, that those areas had higher incidence for flu than other areas in the same region in California. And so income also seemed to have played a role in infecting the disease. And something that was really interesting, which was unexpected for us, was population density had almost no role in the disease, which is something that we were expecting population density to have a bigger role in the disease spread, but it appears that the household size was actually the driver. So now going back to the face mask, which is what we wanted to kind of study, here's the impacts of face mask. And so we decided to explore a lot of different scenarios. And for some scenarios, we said, there's no one is wearing face mask, and so that's the curve in red. And then the epidemic curve here is for the new infections for people that actually wear face masks. And this is taking into account the low acceptance rates and our assumptions that I kind of presented earlier, even though we explored different types of assumptions. So basically, people who tend to wear a face mask are less likely to get infected, and so their epidemic curve is going to be lower. Some of them still get infected, but at a lower rate, whereas people that don't wear face masks tend to have a higher infection rate. And here we also explored different scenarios, which is the baseline, it's no one is wearing a face mask. Then we have only adults, and then in the next one it's everybody wears face masks, children, adults, and seniors. And so you can see that not only the epidemic curve is lower, but it's also delayed. The peak is kind of pushed it's pushed a little bit here. And so that by extending the epidemic spread, then you can have the ability to have more resources, so you don't have all the cases happening in a short period of time, and so the resources can be used to mitigate the impact. And so here is another, the results from other simulations that we ran, this is face masks plus hand sanitizers and face masks plus social distancing. And so you can see for different scenarios, we in different assumptions about how many people are adopting these kinds of behaviors, we have different percentages of clinical attack rate, which is the CAR. And so so the takeaway message, I think, of this study was that face mask and hand hygiene and social distancing, although they're not perfect, they can still lower the overall incidence of cases, and they can be an effective mitigation strategy, especially in the absence of vaccine or some other treatment. Okay, let's see. Okay, so another thing that we also decided to explore was school closures, which is something that could potentially be implemented during a pandemic or an epidemic. And so here, we consider very drastic school closure, which is 5 months, 8 months, and 11-month school closure. And although that seems like it would probably not be a realistic mitigation, because 5 months seems like a very long time, we just wanted to see what would be the impact of extended school closures. And some of the reasons, the drivers for that is because for flu, the vaccine could potentially take a long time to be implemented, and so our assumption was that if we close the schools until the vaccine becomes available, then we're going to see what happens to the epidemic. And so here we have for the 5-month school closure, which is where it's shown by this the line in the arrow, the black arrow. And so we closed the schools, and then the vaccine, we assumed that the vaccine became available, and then we reopened the schools to see what would happen. And it turns out that whenever you reopen the school, because not everyone has been vaccinated, then you have a second wave of infection. And so that's what you see here, that there's a second wave here. In the second scenario, we decided to close the schools for 8 months, and then you still were able to see a small second wave later into the second year. And then we had to close the schools for 11 months in order to not have a second wave show up in the simulation. And so I think these are some of the things that need to be considered, that whenever you relax the mitigation strategies or you reopen schools, that there's a potential for second waves of infection, because as long as there are people still infected in that community, you're going to continue to have transmission. And so that's just something to keep in mind. And then also we consider fear-based social distancing. And so this is something that could potentially also happen, which is, what if a lot of the population just decides to self-isolate because they're afraid of getting infected? And so in this scenario, we assume that 50% of the population isolate themselves or quarantine themselves. And so, and then we assume that they come back gradually. And so these arrows kind of show how people kind of gradually start quarantining, and then eventually they also come out of quarantine in a gradual manner. And you can see also the second wave of infection. But what was really interesting is that the R0, it doesn't come back as high as during the initial wave, which the R0 here was close to 2, and it eventually came down. It's still less than 1.5. It's between 1 and 1.5, but yet you still have a second wave of infection, even though the R0 doesn't quite reach the same level that you had in the first wave. And so all of these are things to consider, and although it's this second epidemic wave is less high as the first one. You still have a lot of number of cases that are infected during the second wave. So, okay, so one other thing that I just wanted to show is about number of contacts for all these different scenarios that we have. And so this is the impact of intervention on contact patterns. And so here degree distribution for the social networks that emerge for all of these different simulations. And so you can see that the average contact per person for the baseline is about 22.5. So on average, people have 22 contacts. And if we have 100% school closures, we have the contacts, I believe the contacts are 19.9. And then if we have 50% fear-based isolation, the contacts go down to 8%. The reason for the school contacts, the 100% school closures not bringing the number of contacts lower is because we, in our simulation, the kids, in addition to going to school, they have other activities after school, and we kept those activities because we assumed that people are still going to continue to have contacts, and so it seems like even though the schools are closed, the kids are still somehow managing to have contacts because the parents know each other, or because there's some kind of like shared daycare happening outside of the school setting. So, although I showed a very complicated and extensive simulation, we have also used SIR type models to explore the impact of different mitigation strategies, and specifically the impact of behavior changes on the epidemic. And in this model, it's a SIR type model, and we have two different classes. We have N classes, which is normal, people with normal activities, and then you have the S sub B class, which is people that change their behavior. And so then people can move. We assume that people can move between, having normal activities or having less number of contacts. And then those people can get infected, and eventually they can recover. And so you can explore different types of scenarios having this system of differential equations. And here I'm just showing one particular run for a given set of parameters where you have the population getting infected, and then people start changing their behavior, and so then there is a drastic kind of change in how the epidemic is spreading in that population, and so then you can just measure the impact of the number of people that are moving into the behavior change class, and what that can impact the overall epidemic. And so, so now just to kind of conclude this part, and before I go into the second part, which is what we have been doing for real-time forecasting of infectious diseases. And so here, basically, some of the takeaway messages are that there's going to be geographic differentiation in any community where you have disease, right? And as I showed, in our simulations, we have areas that have hotspots, and those are driven by many demographic factors, such as income, such as household size, and also the presence of children. And so that's something that we need to take into consideration when we are modeling infectious diseases. We also, another takeaway message is that non-pharmaceutical interventions can be effective in lowering the overall spread, even though they're not 100% effective like vaccines. They can still lower the overall epidemic impact. And one of the other takeaway messages is that relaxing interventions before the number of cases is completely gone will probably result in additional waves of infection. And so, so that's just something to consider when we are thinking about implementing mitigation strategies to halt the spread of disease. And so now I just wanted to touch on some of the activities that we have been doing and using to forecast influenza in the US. And so we have been using clinical surveillance data in Google and along with statistical models to forecast disease with quantified uncertainty. And the CDC, the US has been carrying out a forecasting challenge since 2013. And so every year they have tried to recruit different research groups from the United States, and also even there are other research groups from outside the United States that are participating. So they have about 30 probably groups that every year participate in this challenge. And so basically the structure of the challenge is that it starts in late October and runs through mid-May. And they provide the influenza-like illness data each Friday, and the forecasts are due the following Monday. And I will touch on what are the four different metrics that they're interested in forecasting. And so every week you have to submit one forecast, and so you start late October all the way to May. And regardless of whether it's Christmas break or any other kind of break, you still have to submit a forecast. So that's one of the challenges. And so for our group, we decided to use Google search queries and clinical surveillance data. And the reason why we wanted to use Google is because in the US, the influenza-like illness data that is provided on every Friday, it's usually 2 weeks lagged. That means that whatever they publish on Friday is what happened 2 Fridays ago because of how the influenza network, surveillance network works, and so everything is delayed. And so we have 2 weeks that we don't really know exactly what's happening, and since we are forecasting into the future, then we would like to know what's happening, what happened during those 2 weeks. And so in order to fill that gap, we have been using Google searches to account for the activity that people are searching for. And so the hypothesis behind using Google is that people tend to go online and then they're self-diagnosing and they're looking for information related to the flu, and that actually correlates to the number of cases that are actually showing up in the clinical surveillance system. And so our model, we developed a Bayesian model that combines the susceptible-infectious-recovered dynamics with stochastic patterns and the Google search queries. And so here is sort of a cartoony representation of what's behind the model. So this is the influenza-like illness data that you have, and that's what we want to be able to forecast. So the way the CDC challenge works is they rank everybody's forecast against the ILI data that is provided by the CDC. And so you have an SIR model that sort of captures the complexity and the dynamics of the influenza-like illness, but it doesn't quite capture everything, and it's too smooth and doesn't really capture the complexity that you have in the data. And so in order to add noise to our model, we added 2 different discrepancy terms. One is the common discrepancy and the individual discrepancy. The individual discrepancy accounts for each state is going to have different dynamics, and so that is going to be individual for each state. And then the common discrepancy has to do with how the season works, and which is common across the different states. And so some of the things that we wanted to account for is, for our SIR model, it always wants to go to 0 once the epidemic ends. But in reality, the flu never goes down to 0. There's always going to be some level of influenza cases in the population throughout the year, even though the season runs between November and May. And so in order to force the model not to go to 0 and to kind of stay at some levels, then we added these discrepancy terms. And so using this approach, then these are some of the data and the results that we get from our model. So these are the 4 different metrics that the CDC collects every week when you're participating in the challenge. They want the season onset, which is when the epidemic is going to start, when the number of cases is going to cross a threshold, which this threshold is provided by the CDC, and so they want to know the week when the number of cases will cross the threshold. That's the first metric that they're interested in. The other piece that they're interested in is peak timing, which is the week when when the epidemic will peak in the U.S., also by state, the intensity, and then also 1 to 4 weeks ahead intensity. So you have to provide 1, 2, 3, 4 data points, and those correspond to the intensity for the following 4 weeks. So if you're submitting your forecast on Monday, then you have to say how many more cases you're going to have in the following 4 Mondays, basically. And then here you can kind of see our model, and in gray it shows the uncertainty that we had provided in our model, and then how as the epidemic progresses, the model gets updated because you get new data every week. You're getting new data, and so you can update your model, and so then you can see that at the beginning the model wasn't really capturing what happened, and what happened is in those open circles. But as we got more data, then the model got closer and closer to what happened in reality, and so we were able to capture that. Okay, so then, and so this is the FluSight. This is the CDC website, and I actually tried to log in from here from Brazil, and it doesn't seem like it allows you to log in, and so I don't know if it has to do with the fact that I'm in Brazil, and I don't know if you need to have like VPN in order to pretend like you're in the US, but I don't know if the website wasn't working when I tried it. I wanted to take a picture of what it looked today, but I had to use a figure that I had from a past epidemic, and so yeah, I don't really know exactly if you guys are able to access that website or not, but in any case. This is basically how it looks, and here are the regions, but they also have the states, so you can you have the forecast by regions or by state or by national forecast, and then you can kind of see all the different teams that are participating in the challenge, and then you can see the different data that each team provided for the following 4 weeks, and so you can kind of see which team seems to be closer to what's currently happening. And so one of the questions that I get asked a lot is, why do you guys use internet data, and is internet data useful in some of the modeling activities that you guys are doing? And this is a figure that kind of shows the value of internet data. And so here I have 2 different figures. The top figure doesn't have internet data. It just has the average forecast for a model with the uncertainty in gray. And in the bottom figure, we have Wikipedia access logs and for flu. And then you also have the forecast, and then the uncertainty in gray around the data. And so, for this particular case, you can see that because the data that we get from the CDC is 2 weeks delayed, then our model has to rely on this data in order to provide the forecast. And for the bottom figure, we had 2 additional data points that we could provide to our model. And so then these 2 points basically were telling the model that the epidemic was decreasing. And so, so then you can see that not only the forecast, the accuracy of the forecast increased, but also the uncertainty collapsed around the forecast. And so it seems to us that internet data has been able to provide, to help us have better and more accurate results than if we don't really use internet data. And so, so now so we're trying to, in summary, we're trying to develop new tools to extract useful information from different data streams. And we're also trying to develop approaches to assimilate new data and validate our approaches by forecasting epidemics. And so by participating in the FLU challenge, then we are able to actually assess how well our models are doing and improve them if needed. And our ultimate goal is to contribute towards a global disease forecasting center that can use mathematical approaches and heterogeneous data stream to forecast all diseases around the globe. And so we hope that some of these tools can potentially be used towards the realization of that goal. And so that's all I have. Thank you.
Thank you. So we have time for questions.
Thank you for the talk.
Sure.
Great. Do you think that this internet data is, you can use this forecasting in poor countries where internet access is limited?
So we have, yeah, that's a very good question, and that is one of the challenges. So we have been able to use internet data for countries like Thailand, for example, where the internet penetration in Thailand is about 30%. And so it's, we are able to use to forecast dengue in Thailand. That works. However, in Africa, for example, most of our models don't really work because the internet penetration is very, very low. It's, I don't know, 5% or lower. So it is, no, you cannot really use internet data for very poor countries that have very low internet penetration. And so we think that there might be other ways to use, other data sources that can be used, such as, and Carrie will be talking about that tomorrow, about using satellite imagery to assess, for example, vegetation. And so that's something that, you don't really need to rely on the internet. Climate data also. But in terms of behavior, then it would be very hard to account for behavior because that's usually not collected in any systematic way.
Just one more.
Mm-hmm.
What is your feeling about Brazil in this case?
My feeling about Brazil?
Do you think Brazil has an amount of internet data?
Oh yeah, so in some parts of Brazil it works well, and I don't know if Carrie will talk about that tomorrow. And so in some states, you have very good internet penetration and you can use it to forecast dengue. But in some areas in the north, for example, the internet penetration is low. And so you can't generalize it for a whole country. I think you have to look at very locally to see where it works.
So it's impossible to avoid to ask you, do you have any take about when this new pandemic is going to find its peak?
For coronavirus?
Yeah.
No, I don't. That's one of the crystal ball questions I don't have answers for.
Fantastic talk, and sign me up for the Global Center for Forecasting.
Okay, absolutely.
And I have a lot of questions, but my main question is, when the point of forecasting, I would imagine, or one of the points, is that you can give timely information to the implementers in order for them to change their activities or respond to an incoming epidemic. So do you have any examples of when that's happened, or what are the challenges in terms of the lead-in time that the program would need compared to the amount of uncertainty you have about the prediction at that point?
So right now, with the CDC challenge, we're predicting 4 weeks ahead, and so that's a month that gives policymakers and also hospital officials to use the information if they know how many cases they're going to have in 4 weeks. However, this information is being published on on an open public page, but we don't know exactly how many public health officials are checking the forecast, and so that's another study that the CDC is trying to do in terms of quantifying the usefulness of the forecast when changing their approaches and how they manage the hospitals, for example. And once and whether 4 weeks is good enough, or do they need 8 weeks in order to, to make decisions. And so I think that's still at its infancy, and we don't really know exactly how much the forecasts are currently being used, and so I need to get back to you once the CDC collects the information on how people are using the forecast.
Hi, Sara. Thanks a lot for your talk. It was very interesting. My question is the CDC also, as part of the FluSight or in parallel with it, also evaluating sensitivity analysis on the definition of the epidemic threshold, for instance, for influenza? Or is it still on the same, they used to do 2% of the total cases of the last, I don't know how many seasons or something like that?
As far as I'm concerned, it's still the same. I don't really know if they're planning to change it. Yeah. I'm not aware of that. Yeah.
I'm curious about the mathematics of the model. If you have these agent-based models and you have different individuals at individual level, I agree there's stochasticity at the individual level. Yes,
absolutely, yeah.
But when you go to global properties, at which point these things are deterministic properties and which things are stochastic? Do you have an understanding of the mathematics and
the agent-based simulation, everything is stochastic. Everything, it's basically your,
right,
for the agents, they have itineraries, but they can deviate from their itinerary. And so I guess they can deviate within a certain range, because for a child, for example, you can say, you can go to school with a certain probability. You can also go maybe to the playground. You can stay home. And so you are, in a way, deterministically assigning those different activities. They obviously cannot go to work because they're children, right? And so a work activity will not be part of their profile. But within those different options that you give them, then you basically kind of flip a coin, and then the simulation decides kind of which of those different activities they're going to undertake for that particular day.
I understand, but this gives you at the individual level.
That's correct.
When we are looking at global properties,
right?
So you do that a lot for the gene networks. You can start with every gene being stochastic, but you may have some phenotypes that are absolutely deterministic, right? So
I think that's the beauty of the simulation, is that you assign individual properties, but then you have emergent behavior. And so the hotspots, for example, is an emergent behavior that, we didn't say these populations should have a higher probability of infection. You just say, they have a higher household size, they have more children, and that somehow plays a role in how disease spreads in that community because of those properties. But you're not really assigning higher probability of infection to them.
So if I look at your LA map, that you're showing the map of Los Angeles at this point, if I run two different simulations, the hotspot's going to be always the same place, no matter what you do?
No. It's going to be different, but the hotspots are going to be similar, but it's going to be different rates of infection. And so I was just showing the average for one particular set of simulations, but you are going to have different results based on, because it's stochastic, and so every simulation is going to be slightly different.
One last question.
Hi, thank you very much for the talk. I really want to know if you have included anything about temperature or, equator distance and how that variable could impact the model and that stuff with temperature.
Yeah, for this particular model, we haven't accounted for temperature or any climatic factors, but for models of like dengue, for example, mosquito-borne diseases, we have accounted for temperature and precipitation and other climatic behavior, factors that can potentially impact the spread, but not for flu. Even though there are studies that show that flu is also dependent on temperature, but not for this.
How much? Do you think it's high?
For flu? Well, obviously there is some temperature-related drivers because at least in the U.S., it spreads during the winter, and so clearly, and so it's seasonal. We see it coming back every winter, and so perhaps the winter months are more are better for the virus to spread than in the summer months, and because of the sun and the temperature, I guess, in general.
So how about migration? Because you show some LA, so a lot of tourists go there. You do.
So we don't. Well, we use flights within the U.S. We use the airline, but if there are tourists that are coming by car on the ground, we're not really accounting for that for those kinds of introductions.
So thank you again, Sara.
Okay, sure.
We now have a short break of 10 minutes, and we come back in 10 minutes.